Right, question 7 refers to the same picture, and this time you've got an extra weight, 2.5 newtons, suspended from the rule at the 400mm mark. So that's going to be providing an extra anti-clockwise moment. So you go right back to the beginning, total clockwise moment equals total anti-clockwise moment. Only this time, when you do the clockwise moment, it's still 5 newtons, but now you don't know the distance, because you're going to be moving this 5 newton force. When you do the anti-clockwise moments, you'll have W, which of course you had to calculate in the previous question, and you'll also have this extra 2.5 newton weight, which is 400mm from the end. So you've got two forces giving anti-clockwise moments. You've got the one force giving the clockwise moment, and it's got a new distance. You have to work that new distance. For question 8, we have a meter rule balance at the 350mm mark by putting a 3 newton force at the 10mm mark. So there's part of the diagram. I think the key thing to getting going with this question is to complete the diagram. What force is missing? Well, it's the weight of the ruler, and because it's an ordinary, straightforward, uniform ruler, whereabouts does the weight act? And obviously it's going to act at the centre of mass of the ruler, which is halfway along the ruler. And that's what we're trying to find. We're trying to find the weight. So just as before, we're going to use the principle of moments, and we're going to write it out in full. Total clockwise moment equals total anti-clockwise moment. And it should be a straightforward question, because you've got one force that tends to turn it clockwise about the pivot, one force tends to turn it anti-clockwise. Quite straightforward. And then the second part of the question, calculate the support force. So you'll have two forces acting downwards, but the ruler's in equilibrium. So what does that tell you about the upwards force which acts at the pivot? Question 9 looks a bit more complicated, but if we can do a diagram for that, it should be quite straightforward. Because I think if this board was to topple, where would it pivot? It would pivot about the edge of the pool. So all we have to do is draw the diagram, and the edge of the pool we're going to represent there by a little triangle to be the pivot. What forces would tend to make it turn clockwise? Well, there's the weight of the diver, and there's also, it tells you the weight of the board. And it tells that the board is uniform, so we know whereabouts the weight of the board acts. Halfway along the board, which I haven't drawn very well, but never mind, that represents halfway along the board. So the diver, the weight of the diver and the weight of the board are both making this board tend to rotate clockwise about the pivot point there, but it doesn't. What stops it rotating? Why doesn't the board spin round? And it's because the bolts are holding it down. And because the bolts are on the other side of the pivot, the bolts are providing a moment in the opposite direction. So there is the situation, put the values in, calculate that downward force provided by the bolts. The second part, once you know that, you know all three downward forces. And the question is, what's the force on the edge of the swimming pool? Well, the swimming pool, at the edge of the swimming pool, is holding the whole thing up. So you've got three downward forces, one upwards force. It's an equilibrium, so it should be quite easy to calculate that upward force. So question 10 is about a uniform beam. I've sketched the uniform beam. It says it's supported at each end. So I've drawn a support force upwards acting at each end. I haven't labelled them, you should label them. And we say it's uniform beam, and we're told the weight. So we must draw the force for the weight. Because it's uniform, we should know whereabouts we need to draw that weight. We're going to draw a downwards arrow to represent the weight. It's uniform, so you can work out for yourself where on the beam you draw that downwards arrow. And you've also got a person of weight 500 newtons. So you need to draw a downward force of 500 newtons representing the position of the person. Right, once you've done that, you've got to calculate the support force of the beam. You're going to do that by taking moments. And what I suggest is that to find the upwards force on the right hand side, you take moments about the left hand side. That way, this force here doesn't have any effect on the moment. The only anti-clockwise moment will be provided by the force on the other end, and there'll be two forces providing clockwise moments. The forces I haven't drawn on, because that's your job, the two downward forces because of the weight of the beam and the weight of the person. But please remember, it's a question on moments, it's using the principle of moments, so please begin the question by saying total upwards moment equals total downwards. Forget that. Please begin the question by saying total clockwise moment equals total anti-clockwise moment. And I haven't got time to edit that out. Question 11 gets off to an easy start because it tells you what the load is at the middle and it tells you how much force is on each pillar. And it asks you to calculate the weight of that horizontal span. So that should be quite straightforward because we know that the total weight of the load and that span is equally shared between the two pillars, and you know the force on each pillar, therefore you know the total downwards force, so therefore you're able to work out the weight of the beam. Part B becomes a moments diagram, and again it starts by asking you to do a free body diagram. So a free body diagram would show the beam, it would show the upwards forces at each end, and it would show two downwards forces. One of them, the actual weight of the beam itself, or the part of the span of the crane, the weight of that beam, and then the other one would be the weight of the load. Once you've done that, you're going to use the principle of moments, just like in the previous question. Start by using the left-hand side of the crane as the pivot, in which case the anti-clockwise moment is provided by this force. When you've done that, then you can use the other side and take moments about this point to find that force. But please, it's a principle of moments question, so please begin by writing total clockwise moment equals total anti-clockwise moment. Question 12, I'd start by drawing a diagram. This time the supports 0.8 and 1.2 metres from each end, so it's not symmetrical. You can still draw the diagram straightforward with the upwards forces and the downwards forces and use the principle of moments. And the obvious places to choose as the pivots would be the two support forces. So you have to use the principle of moments twice. Using the left-hand support will let you find the force on the right-hand support, and then if you use the right-hand support as a pivot, you can find the force on the left-hand support. And for part B, you've got these curtains which are sort of uniformly distributed. So if you think about where that force would actually act, 90 newtons distributed uniformly along the whole length of the pole. Think about where you could draw that as if it was concentrated. For question 13, I've started the diagram for you, but there are other forces. There are two more forces to be added to that diagram. When it comes to finding the tension, it's just actually very, very easy, and you don't even need to use all the information in the question. There's like a shortcut way of working out what that force would have to be, which doesn't involve you even using the length of the girder or the height of that end. If you can sort of spot the relationship between two of the lengths, You actually don't need to know what either of them are. And for the last question, let's just think about components. There's tension in that string, there's tension in that string. Each string has got a horizontal component of its tension and a vertical component. And think about the picture. We know the weight of the picture, which is acting downwards, so we also know how much upward force must be required. And if we know the upward force, we can find the vertical component for each half of the string. And when we know its vertical component, we should be able to find what the tension actually is. And that's probably completely jumbled up, but I don't care because I'm going skiing now, and I'm not bothered.